Hi, good morning. This is our second section on fundamentals of logic. So, in this section, we discuss mainly about logical implication and validity of arguments. So, we start with what a logical implication is. So, the general form of logical implication or an argument, general form of an argument is something given like this: P1 and P2 and P3 and etc. Pn. So n primitive statements is implies Q. So a number of primitive statements implies uh, another statement Q. And here P1, P2, etc. Pn are known as premises, and Q is the conclusion. So if you have n statements, then we can conclude that another statement Q is true. And this particular statement is said to be a valid statement if all the premises P1, P2, etc. Pn are true, then the conclusion is also true. If all the premises are true, then the conclusion is also true. In that case, we can conclude that the argument is a valid argument. No other combination is important. If any of these premises is false, then the conclusion may be either true or false. Then, so here we can have an example. Ben's car keys are in his purse or they are on the table. And Q is another statement. Ben's car keys are not on the kitchen table. So we have two statements, and there is another third statement. Therefore, Ben's car keys are in his purse. Ben has a car key and is either on the table or on the kitchen table. Then another statement Q, the car key is not on the kitchen table. Then obviously it is on his purse. So this is a valid argument if P is true and Q is true. If the statements P and Q are true, then R is obviously true. So that is can be represented as P and Q implies R. So this is an example of a valid argument. So what we check is about the nature of P and Q or the premises. So we have to examine the cases when premises are true, and whenever the premises are all true, then the conclusion is also true. Then the testing of validity of an argument. Then we already discussed that an argument is said to be a valid argument when all premises are true. Then the conclusion is true. So we are not bothered about the case when one or some of the arguments are false. So we don't have to consider the cases when at least one of the premises is false. That combinations are not important in our discussion. We consider the cases when all the premises are true. So that will reduce our effort to check the validity of an argument. That means we don't have to form the entire truth table of the argument and check whether the implication or the statement is a tautology or not. So that's another method. We just construct the truth table of the left hand side and right hand side, and or the premises and conclusion, and observe the truth table and check whether whenever P1, P2, etc. are true, Q is also true or not. That's one method. But creating the truth tables for the combination in which at least one of the premises are false is not necessary. Now, another thing is logical implication. This again we can use in checking the validity of an argument. So logical implications. If P and Q are two arbitrary statements such that P implies Q is a tautology, then we can say that P is logically implies Q and we write P implies Q. P then Q or the conditional statement P then Q is a tautology, then we say that P implies Q. Then if and only if Q is a tautology, then we can write P if and only if Q or P is equivalent to Q. So P is equivalent to Q is represented by this symbolically represented by P if and only if Q, or at some case we write P equivalent to Q. So or in other words, if P is equivalent to Q, then P implies Q and Q implies P. Or in other words, P implies Q is a tautology and Q implies P is a tautology, and P if and only if Q or P biconditional P if and only if Q is a tautology. In that case, we write P implies and implied by, or P is equivalent to Q. Then using all these ideas, we can eliminate the construction of a truth table from the process of testing the validity of an argument. So to test the validity of an argument, we just need to check the cases wherein all the premises are true, and hence we consider the conclusions of rows for which are solved once. And the truth of inference and are fundamental in the development of step-by-step validation of how the conclusion Q is logically obtained from the premises. So using the rules of implication and equivalence, we can develop a procedure for step-by-step validation process or step-by-step procedure by which or how to check how the conclusion Q is obtained from the premises. So instead of constructing the truth table and observe the truth value of conclusion corresponding to the premises with truth value 1, all premises with truth value 1, we can develop another method in which we obtain the conclusion from the premises in a logically correct step-by-step procedure, and that is more logical method to obtain the conclusion. Now here we will come across a number of rules which can be used in testing the validity of an argument, or which can be used to obtain the conclusion from the given premises. So first one, modus ponens, P is given and Q implies P implies Q is given. This is not Q. This is the typo. It is P implies Q, then Q. If P is given, then P implies Q is given, then Q is true. So it's a simple, very obvious one. P is true, P implies Q is true, then we can conclude that Q is true. So this is a simple method to make an argument. And this next one is law of syllogism. P implies Q, Q implies R, then P implies R. If P implies Q, Q implies R, then P implies R. Then modus tollens, all these names are from, I think it is from Latin. P implies Q, negation Q, then we can conclude that uh, negation P. P implies Q. P, if P is true, then Q is true. But we have negation Q. So the Q is false. Then obviously we can conclude that P is also false. So in this can be uh, combined with the argument P implies Q and negation Q implies negation P are equivalent statements. Okay, anyway, that is modus tollens, and then conjunction, that is P and Q are true, then P and Q are true. Distinction syllogism, disjunctive syllogism, that is P or Q is true, and negation P, that is P is false. Then obviously Q is true. Either P or Q or both are true. That's the meaning of first statement. And the second one, negation P, means P is false. So the only possibility is Q is true. So conclusion is Q is true. Then rule of contradiction. If negation P implies tautology, contradiction, then P. Negation P implies tautology, false fallacy, or the contradiction, then obviously P is true. Then another rule which we can use is conjunctive simplification. P and Q. If P and Q are true, then P is true. Also, we can write Q is true. That is known as conjunctive simplification. Then destructive amplification, that is P, then P or Q. P, if P is true, then P or Q is true. We already know that P is true, then P or Q is also true. Then rule of conditional proof. P and Q, P and Q is given. Then P implies Q implies R. P implies Q implies R. Then obviously R is true. Now another one, rules of inference, proof by cases. P implies R, Q implies R. Then P or Q implies R. If P implies R and Q implies R, then P or Q implies R. Then constructive dilemma. P implies Q, R implies S, then P or R. Then we can conclude that since P implies Q and R implies S, and P or R is true, then we can conclude that Q or S. That is constructive dilemma. All these are some fundamental rules by which we can check the validity of an argument. And there is another one, destructive dilemma. P implies Q and R implies S, then negation Q or negation S, that implies negation P or negation R. So that is destructive dilemma. All these rules can be used to check the validity. Then the rule of contradiction is a basic method for establishing the validity of an argument. It is known as proof by contradiction. So that's a method to prove a result, or in fact disprove a result. For example, the famous Fermat's theorem. It says that for integer values of x and y and z, and integer values of n greater than 2, the equation x raised n plus y raised dn is equal to z raised dn has no integer solution. This is the famous Fermat's theorem. So we know that for n is equal to 2, it is x square plus y square is equal to z square, and that equation has a number of integer solutions, and they are known as Pythagorean triplets. But uh, whenever n is greater than 2, the equations like x cube plus y cube is equal to z cube, or x raised to 4 plus y raised to 4 is equal to z raised to 4, has no integer solutions. And this is a conjecture, and which is proved by Andrew Wales in uh, recent days, and I think in 98 or 96. Okay, anyhow, um, this particular equation, throughout the history of this particular equation, many of the mathematicians are trying to find out some counter examples, some triplets of x, y, z which satisfy this particular equation, and that is a method to prove or disprove um, theorem, and this is known as proof by uh, counter example. And here there is another method. So this is a simple method by which we can prove or disprove a theorem. And in a similar way, uh, the proof by contradiction is another method by which we can prove a result. So if you have a system of argument which is like say P1 and P2 implies some conclusion Q, or if you have a number of statements P1, P2, uh, okay, like this P1, P2, P3, etc., Pn, the premises implies the conclusion Q. This is a simple argument. Then proof by contradiction. We assume that all the premises are true, and we assume say negation Q. Then if this combination leads to contradiction, if this combination of premises plus negation of the conclusion leads to a contradiction, then which means our starting point is wrong, and the starting point is wrong is only if the premises is always true. We cannot change the truth value of premises, but what is wrong is in our assumption that negation Q is true, which means Q is true. So this method is known as proof by contradiction, and that's again a powerful tool in proving results in mathematics. So that's the proof by contradiction. So we can consider simple examples like um, say root 2 is irrational. So here we give the proof by assuming that if possible root 2 is rational. So we assume that root 2 is equal to a rational number, say p by q, and if we make a number of simplifications, then this argument leads to a contradiction. Okay, we will discuss this particular case in our next sessions, and for the time being you may go through this particular case or start with the statement as root 2 is equal to p by q, and try to obtain and a contradiction that uh, which contradict our assumption that P is a integer, Q is another integer, and P by Q is a fraction or rational expression in its simplest form. That means P and Q are prime to each other, or they have no common factors. And try to obtain some contradiction from the expression that root 2 is equal to P by Q. Then counterexample, we also already discussed about the concept of counterexample. In order to prove that a particular result is false, we don't have to give much examples. Only need one particular example for which the result is false. So that is counterexample, and uh, these are the methods by which we prove the validity or check the validity of an argument. And we will have to go through a number of arguments to be familiar with this concept. So we will in our next session we will go through a number of arguments and try to understand how we can use the methods of equivalence and implications to check the validity of a particular argument. So for the time being, you just go through the uh, proof by contradiction, and this is a simple example, simple case. Root 2 is rational, and the contradiction can easily obtained by just squaring this equation and rearranging the terms and using the fact that if we have an even number that can be written as 2 into m, etc. So just try to obtain a proof of the theorem which says root 2 is an irrational number using the method of proof by contradiction. So for the time being, that's enough, and thank you.